Okay, so what we discussed last day is basically a very brief introduction to classical computing, and today we'll also continue that, and hopefully we'll start quantum computing or maybe quantum mechanics today. So last day what we discussed, I mean, we ended with the concept of what is called, so we basically discussed there are two models of computation. So models of computations, and one of these was the Turing model, the Turing machine, and other one is the circuit model, the circuit model. And among these two, circuit model is close to the reality. Okay, and finally we talked about a problem what Hilbert asked is like, can you have an algorithm which can we can solve all possible problems? Okay, and we said that okay, this is not possible because of this theorem due to Gödel, which proves that in any mathematical logical system there are propositions which are undecidable. That means we don't know whether it's true or false. Okay, it cannot be decided. Okay. Then the question here is, then which problems are computable in a machine? Okay, so here is the question. So which problems are computable? Or you can say solvable. Not exactly solvable, but let us focus, since we are focusing only on the theory of computing. So let us say which, because a problem is a function for us, as we defined yesterday, last day. The function is nothing but, I mean, a function can be represented, a problem can be represented as a function from the input space to the output space. So then essentially, if we ask that which problems are computable, basically it's solvable, it is equivalent to saying which class of functions are computable. So which functions are computable? And so people spend a lot of time during that time to answer this question. This is a realization, okay, after a lot of research, okay, and this realization is known as the famous Church-Turing thesis. So this is called the Church-Turing thesis, which states that, okay, and so the class of problems, okay, are the class of functions which are computable by a Turing machine is equivalent to the class of functions which are computable by using an algorithm. Okay, so the class of problems that are computable is equivalent to the class of problems okay, are equivalent to the class of functions, okay, that are computable using a Turing machine. So that means if there is any function which you want to compute, so then essentially in using a Turing machine, so then that function is computable, otherwise it's not. So, and in fact, using Turing machine, one can solve a big class of problems, okay? And this thesis actually, I think it was around 1936, okay? And this thesis till now, okay, has not been disproved, okay? So everybody believes that this is correct, okay? So till now, not disproved. So now there is another model of a machine, Turing machine, and this is called, I'll just mention this, which is called probabilistic Turing machine. Because I need this word little later, probabilistic. So here in this model, what we do is probabilistic Turing machine, that all the states in the Turing machine, they appear with some probability. I mean, if you just read a little bit about a Turing machine, then you can find it more like what do you mean by state, okay? So then the states are here, okay, occur with some probability, and it is called a probabilistic Turing machine. Now, I'll talk about, so this is about the Turing model. Now I'll talk about the circuit model. Circuit model of computation.
Sir, can you go back at once? So, in the church Turing thesis, you told the class of problems that are computable is equivalent. Did you mean to say the class of problems that are solvable is
Solve,
equivalent?
yeah. I mean,
Okay.
yeah. So yeah, the same thing. Yeah. So now, I mean, problem is equivalent to a function. So I mean, basically what you have is, as we discussed last day, so what you have is you have some function from 0 1 to the power n to 0 1 to the power d. And yeah, so this is what it is. So this is what a problem is. So if you can compute, so when we say a function is, if there is a function, there is an input, then if you find out the output, then we said that, okay, you compute that function, okay? But the function is equivalent to the problem, so it is the same thing. Yeah. Okay, now in a circuit model of computation, okay, so basic primary unit is the bit, okay, it's a classical bit, which can, as we said, which is like, can take two states, which is 0 or 1, like on and off, okay. And by circuit means it's a something which is made of wires and gates, okay. So circuit is nothing but, okay, it's made of wires and gates. There is something called gate. So what does this wire do? Okay, so the wire carries information. So one bit of like a bit. Okay, so it carries some voltage, let's say something like that. So it carries information or a bit of information, because bit is used in two different contexts. One is it is a unit, and like how many bits, okay, this is used in two senses. So one is the unit, how many bits, like the content of information, okay, in something in a random variable is measured as how many bits, okay. And bit is also represented as 0 or 1, so it is used in two different aspects. So carries a bit of information, okay, and this gate information, and what is the use of this gate? So the gate actually performs some logical operation. So you can consider this as like there is some input and there is a way of processing the input, okay, and then ultimately you have to perform some operation like addition or something, some kind of operation, which today I'll discuss a little bit. So this is performed by the gate, okay. So performs the logical operations. And I will also discuss, I'll give you some examples of this logical operations. Okay. Yeah. So, and I'll just assume that you know, because there, okay, the prerequisite of this course is a little bit about computing and a little bit about information. Okay. So, so I'll assume that you know that anything is there in this world that can be converted into strings of 0 1s. Okay, and how it can be done? Okay, I will assume that you know this. You can just type it in Google. Okay, so or you can follow some lectures in information theory, or or you can follow any book. Okay, so yeah, so any book on information, classical information theory will give you the idea. Okay, how to generate, let's say, strings of 0 1s from letters or from messages, from anything actually. Okay, so because we process this kind of information using this strings of 0 1s. But what is obvious is like if you have an integer, okay, then that can always have a correspondence with this strings of 0, 1 if we just take the binary representation of that positive integer, let's say. Okay, but same thing you can do for all kinds of numbers. Okay, so like negative negative integer, or let's say real numbers, or maybe rational numbers, so you can do that. Okay. Yeah, so it's 0 and 1. So this is very interesting that 0 and 1, they are like, you can assume that they represent voltage in a physical device like a transistor. Okay. Now, so now I'll talk about this gate. I mean, some classical gates, okay, or classical logic gates. So classical, so I'll give you some examples or some classical logic gates, okay. So what happens, as we discussed before, a computation is nothing but, suppose you have a function, so you want to compute, so that means it is, you have some input, which is like a string of 0 ones of length n, and it has to produce some string of 0, 1 of some other length, let's say d. Okay. Now, then the question is, so any problem, okay, finally, ultimately can be written as this. If you want to really write this function, I mean, whatever you want to compute, ultimately you have to give some input and then you have to find some output. So in a true computational sense, you are giving a bunch of 0 ones actually as an input. Now the thing is, this can be very, very complex because n can be very, very large because you have to send a big message, something like that. So it could be very, really, really large. So it can be, this function can really be complex. But what we'll do is that we'll try to find some simple, okay, some elementary logic gates, okay, which can be used to perform a very complex, I mean, that can perform the job of a very complex function. Okay, so here is the idea. So idea is using, so in general, f can be complex, f can be complex function, it can be complex, and or maybe complicated would be a better word, complicated, and then we use elementary logic gates to perform. So when I say we'll use elementary logic gates to perform this complex operation, it actually means that we'll do some combinations of this elementary logic gates in order to define the original function in terms of this combination. And then, so ultimately, when you are performing the function f, it boils down to performing a series or sequence of elementary logic gate operations. Okay, so this is what it means. So you use elementary logic gates to perform f, perform the operation of f. Okay, perform the operation f, let's say. Okay, this is how we'll do it. So first, we'll talk about some elementary logic gates. Okay, which will actually, so basically, so this is how it works in the computational world, that if you have something which is very complex, which is very complicated, you divide the problem into simpler problems. Okay, this is the same thing. If you do a course in data structure algorithms, then you'll find that even if you have a very big thing, so the big problem, so your job will be to divide this big problem into smaller problems, into small problems, and then you perform some kind of operations on the smaller problems, and then until it solves the big problem. Okay. Yeah. So first of all, we'll talk about some elementary logic gates, which including, for example, so if I have a logic gates like this function, let's say from 0, 1 to 0, 1, that means the input is a bit and output also is a bit. Okay, so this is kind of a 1-bit logic gate operation. Okay, and the simplest one is called, so this gate is called the identity gate. Okay, identity gate means what? Identity gate means if the input is 0, okay, so this gates, okay, I'll define using something called a truth table. Okay, so here if this is the input, okay, input, then this is the output. Okay, output. So let's say I give input as a, let's say this is 0, and output also must be 0, and if input is 1, then output is also 1. So this is called the identity gate, and this circuit, okay, in an abstract sense, it is, I mean, this gate in abstract sense, it is denoted as this. So if A is the input, then A is the output. So an A here could be like in 0 and 1. Okay, this is an identity gate. This is the identity gate. Okay, that means whatever. So this is a gate which doesn't do anything. Okay, whatever the input, it returns the same input as the output. Okay, and another gate is which is called NOT gate. Okay, so this is called NOT gate. Okay, in the books, you will find that this not means they will write in capital letters. Okay, so I'm writing a small letter, but it is equivalent to the same thing. Okay, so here in the NOT gate, the truth table is like if I give input as 0, then output must be 1. If I give input as 1, then output must be 0. So then this logic gate, I'll just write like if input is A, then the output is A bar, which means 1 minus A. So minus here means I'm doing this binary arithmetic here. Okay, so if it is 0, then it is 1, and if it is 1, then it is 0. And here this gate is drawn like this. So this is called a NOT gate. So this is A, and this is A bar. Okay. So these are the two gates which are this. Our input is a bit and output is also a bit. And now we'll consider some logic gates where it can perform this kind of operation where you can have 2 bits, okay, as input, and output is 1 bit. Okay, so my first gate example of the first gate is called something called AND gate. AND gate, and this is denoted as this. Okay, so and this is defined as like if you have 1 bit A, another bit is B, so you need 2 bits here actually, okay, to perform this. And I'll write A and B. Okay, or some people it will write A times B because it will be A times B. Okay, I will tell you how. So I'll write the truth table. So it is like, okay, so you have A, you have B, then this is A and B. Okay, so if A is 0, B is 0, then A and B is of course 0. It's just the product, and 0. Let's say this is 1, then the output is 0. If it is 1 and 0, 1 and 0, this is still 0, and this will be 1 only when both are 1. So there are 4 possible inputs here because it is 0, 1 square, right? This is the input space. So there are only 4 possible inputs, okay? Which is like 0, 0, 0, 1, 1, 0, 1, 1. And these are the corresponding output, okay? And this, so if you want to draw this, so it must consider 2 bits as input, and then it is drawn like this, okay? And 1 bit for the output, so it is drawn like this. So this is an example of a 2-bit gate. You can and then another one is like OR gate. So somehow my pen is not working properly. OR gate is okay. So guys, I'm going a little bit fast. Okay, if you have any doubt, you can always ask me. Okay, because I think you know this. Still, I'm just repeating just to recall this thing because I'll do a quantum version of these things. So I need to recall this. So this is OR gate. This is denoted as A or B, and it is like A plus B minus AB. Are all this plus and minus? They are just the binary arithmetics. Okay. So if you take A, and this is the truth table. So and then you write A or B. Then if you take 0, 0, then output will be 0, 0, 1, output will be 1, 1, 0, output will be 1, and 1, 1, output will be 1. And it is drawn like this. So it is A here, B here, and the output is A or B. Okay, this is something called OR gate. Then my next gate is XOR gate, XOR. So this I'll write in capitals, XOR gate. Okay, XOR gate, and it is denoted as this O plus. Okay, so plus inside O. Okay, and this is also sometimes in some books. This is called also exclusive OR. Exclusive OR gate. Okay, and how it is defined? It is just the binary operation addition. So this is A. So A plus B. So because it is a two-bit gate, so A plus B is nothing but A plus B mod 2. Okay. So that, I mean, now I think I don't like to write the, or maybe I will write again. So it is A, B, this is a truth table. And then this is A plus B. So this is 0, 0, then the output will be 0, then 0, 1, 0, 1, then output will be 1, and it is 1, 0, then output will be 1, and 1, 1, output will be 0. This is just a binary operation. And it is denoted as this. So this is denoted as this. So 1 bit output and 2 bits as input. Okay. Okay, and then another important gate is called not AND. So it is called NAND gate. NAND, NAND gate. So, and this is denoted as this. Okay. This is, okay, I'll not write this. It's confusing. Okay. So this is like application of a NOT gate. Okay. To the output of AND. So it is defined like this. A NAND B is equal to AB bar. Okay. So basically it is 1 minus AB. Okay. Bar means the NOT gate. Okay. So it's a complement. So if you have this NAND gate, then truth table is like this. A, B, and A arrow B. It is like 0, 0 will give you value 1, 0, 1 will give you value 1, 1, 0 will give you value 1, and 1, 1 will give you value 0. And it is denoted as this A, B. These are the input bits. And then you have this A upper arrow B. This is the output. And there is one more interesting gate. This is like NAND, not AND. Then you have not OR. So it's called NOR gate. NOR. Okay, and this is the arrow is down. Okay, so this is NOR gate. Okay, so it is like you take a NOR gate of the OR. So it is defined as this is equal to A or B, and then this complement of this, not of this. So ultimately it will be, okay, if I just write expression of A or B, so this will be, I think, A plus B minus AB, and then take the bar of it. So it will be like 1 minus A minus B plus AB. So yeah, so this is the NOR gate. Okay, and so if we just write a truth table of this, so it will be, okay, so let's say A, B, and A down arrow B, which is 0, 0, then it is 1, 0, 1, this is 0, 1, 0, it is 0, 1, 1, it is 0. And this is denoted as this. There are 2 bits, okay, and then we have this and then this. You'll find a pattern actually, okay, of all these diagrams. If you just closely follow, you'll find a pattern, and then you don't have to recall all this, okay. And there is another very, very interesting gate which will be used, I mean, which is very fundamental elementary logic gate, which is called just the copy gate, okay. And copy gate, it is not exactly the input is not actually 2 bits, okay, but the output is actually 2 bits. So it is like copy gate, okay, copy gate, okay, it is like this is a function. You can assume like this is a function, okay. So any gate is a function. So, but this will take, like, if you give a bit, then it will produce a copy of it. So the output is like A comma A, okay. And yeah, so this is denoted as like this, okay. If we give a copy of this, just give a bit, it will produce a copy of this. So it is called the copy gate. And another important gate is like, which is a 2-bit gate, and whose quantum version is very, very important, which is called swap gate. Swap gate, okay. And this is a function which takes, if you give input, like which takes A comma B as input, then it will produce the output as BA. It will swap the bits, okay. And it is denoted as this. I mean, the diagram is like this. This is how it is plotted. Okay, this is A, B, and this is B, A. Okay, So yeah, but the question is, if I have a very complex function, okay, complex function, I want to implement that function in a circuit. And the question is, what are the fundamental elementary gates? What do I mean by fundamental? That means it is a collection of gates which are enough to implement any complex function in this world. Okay, so what is that collection? That if I take that minimal set of gates, okay, then all possible functions can be written as some combinations of this minimal set of elementary gates. And this is a very fundamental concept in computation. And this is called universal gate. So those gates, okay, we'll call universal gate. So this is called universal gate. Universal gates. So when we'll discuss this quantum version, okay, so here the difference will be like here the inputs are the bits, and there the inputs will be qubits, and then the question would be what. So because there you will see all these gates, okay, these are the operations, okay, they will be represented by unitary matrices. The question will be which unitary matrices are important, which gates are important, okay, to perform any complex operation. Okay, so for classical it is known, quantum we'll discuss later. So this set of gates like and or I'm not going to prove it. So not all the proof is not very difficult, but still I'll not prove it. And the copy gate. These four gates, okay, these four gates are enough, okay, for any classical computation of any kind of complex function. Okay, these four gates are really enough. So for the circuit model of computation, basically we need to know how to implement these four in a circuit, okay, or in a chip, let's say, or okay. So if we want to design a system, okay, a computing system, then we need to know a way to implement these gates. And if we know how to implement these gates, and if we know how to store inputs, like how to store strings of bits, and it is enough to give me a machine, okay? Because any function can be constructed, okay, using this four fundamental elementary gates, okay? Now I'll talk a little bit about computational complexity because, okay, so this is also a fundamental part of computing, like how many resources you'll be using to solve the problem. And this is given by it's this idea which is called computational complexity of a problem. Okay, so the idea is how much complex a function is to compute. Okay, in terms of okay some resources like space, time, and energy. Okay, like how much time it will take, how much space will it take, or how much energy it will take. And whenever we deal with complexity or computational complexity, the idea is we want to have minimum resources, okay, to solve the problem with the best possible algorithm. Okay, so there can be many algorithms, but our always goal will be to use the best possible algorithm. Then what is the minimal amount of resources required? Okay, that's the topic of this thing, a computational complexity area. Okay, and here I'll just define one thing. So the big O notation for the sake of completeness, because some of you may not know. So in some places I'll write like something like order of n square, something like this. So what is the meaning of this? I'll just define it. So what is the meaning of this big O notation? Big O notation. What is the meaning of this notation? Suppose I have two functions, okay, of some parameter, let's say n, okay. So suppose f and g, okay, are two functions, okay, of let's say some, okay, let me write it like this, fn and gn, okay. So n, you can assume that n is an integer, positive integer, you can assume like that. So for example, fn could be like n square plus 2, gn could be something like that, okay. Gn could be some to the power n, for example. Okay, so something like that. So it could be any function of n. Then I'll write, suppose these two are functions, and then I'll write, then we write f equals to order of g, so our big O of g, if fn by gn is bounded above and below by constants, okay, when n goes to infinity. So when n is very, very large, fn by gn is a bounded number. It's a finite number, you can say. So here C1 and C2, they're constant. So you can assume like 0 will be bigger equal to C1, less than, of course, it has to be less than equal to C2, and this is finite. So these are finite numbers, okay? For example, if I ask you, I mean, very simple. I mean, given any algorithm in this world, okay, so your job will be, in order to understand how much time or what is the time complexity, okay, of this algorithm, okay. So in many cases, what it is done is this n represent, okay, and this n represents the size of the input in terms of bits. That means, for example, n is some integer, okay, then how many bits, that means how many 0, 1, okay, you require to represent that. Okay, sometimes it is n is considered as the size of the input, okay, in terms of bits, in some binary digits. So then the question will be, in order to perform that algorithm, okay, so how many steps you require, okay, so some people consider order of, let's
So
say,
that
n log n. Yeah, please go
so,
ahead.
so that's your upper bounding as well as lower bounding, right? So isn't
Yes,
that
yes, yes.
big theta of notation, because big omega means that there is just an upper bound, and big omega means there is just a lower bound, and if
Yeah,
there is
I'm just saying, yeah, I'm just saying it a big O notation
yeah, then
altogether.
then there should be just the upper bound, right?
Yeah, but I am making it also lower bound here. Okay, so I can go into the other classes, but for me, for the time being, let's say, I mean, I'll not discuss much about this, but for the time being, I will assume this big O notation means it is bounded above and by bounded below. Okay.
Oh, okay, okay.
So for the timing, I need only require this part. Okay, I mean, I will not discuss the entire complexity issues. I mean, I'll talk about that maybe later, whenever required, I'll define that accordingly. But right now, I don't need anything. Okay, so because right now, I just said, because I need to give you an example to understand what is the meaning of saying that a function is complex. Look, I'm talking about complex, but I did not define anywhere what is complex. Okay, so I'm saying it is complicated or complex, difficult to compute, but I never defined it. So I'll give you an example to understand. Okay, what is the meaning of that? Okay, I'll come to that. So for that, I just only, because there I'll use some notation. So maybe just big O is enough for me. And for there, I mean, in that case, it is bounded above and bounded below, that is enough. Okay. Yeah. So yeah, for example, if I ask you like how much, what is the complexity of multiplying, let's say, two numbers, okay, which have, let's say, both are of n digits, okay, they have n digits and binary digits, okay, in a Turing machine, if you want to do that, so how many steps, let's say, it requires? I mean, suppose, yeah, so if you want to multiply two numbers, okay, which are represented by n bits, then what is the number of steps you require? Okay, so then you have to write this number of steps as a function of that input, that n number of digits. So you have to write that number of steps as a function of that. Okay, so yeah, something like that. So that is an example, just an example. Now, I mean, whenever I say complex problem or simple problem, so in the world of computational complexity, we have basically, we'll consider, I mean, we'll distinguish problems into two categories. Okay, one is if it requires polynomial resources, and the other one is the exponential resources. So there are two classes of problems basically. Basically, I'm saying, okay, fundamentally there are two classes of problems. Two classes of problems. If you want to solve them, okay, so there are two kinds of issues. So one needs, let's say, polynomial resources. I'll tell you a little bit about it, but let me write a polynomial amount of resources. Okay, and another is exponential amount of resources. Okay, guys, just give me a minute. Somebody's knocking my door. Just a minute. Yeah. So basically, two classes of problems are there. One set of problems, it is like it require polynomial resources, and another set of problems which require exponential resources. Okay, and this polynomial resources, like the problems which require only polynomial resources, this kind of problems are considered to be easy. Okay, or let's say tractable. Okay, so these problems, so problems which require polynomial resources, okay, these are called easy or maybe tractable. And otherwise, other set of problems, they are sometimes called exponential resources, okay, or maybe some people will use the word super polynomial resources, okay. There's another word is super polynomial sources, and these are intractable, okay, difficult, complex problems, okay. So difficult, okay, problems. So difficult or intractable. Okay, now just to understand what it means, okay. I mean, what is the meaning of a difficult problem? Okay, so for example, I'll give you an example of a difficult problem. The problem of finding the prime factors of an integer, positive integer, let's say, okay, it is a problem which is a difficult problem. Okay, so finding prime factors of an integer, okay, is known to be is known to be difficult. And
Sir, is it
I'll tell
known
you
to be
just the difficulty
difficult?
level of this problem. Okay, so the best algorithm, yes.
Sir, is it like
Okay,
known
the
to be
best.
difficult, or like someone proved that it is difficult, or there are no easy solutions known?
Yeah, I'll give you the example, and then you'll see. Okay, so let me just finish the example. Okay,
Oh yeah.
so for example, this. Yeah, can you repeat again? What did you say?
Oh, okay.
Okay,
What I,
so
I okay.
yeah. There is some problem in the. I think I mean their voice is not coming. I mean I cannot. I don't understand what you said.
Oh, okay. What I told was, can you hear me now?
I don't hear. If anybody can hear him, so please can you repeat? What is that? I mean I cannot hear you, so its voice is cracking.
Oh, okay.
Okay, so the best possible algorithm. So suppose I want to factor. Let us say I want to factorize an integer n. Okay, this is an integer. The input size will be actually small n, which is actually log n. Okay, let's say this is the input size if n is a positive integer. And if you want to know why, so I mean, you can think about the binary representation and how many bits you require, something like that. So it is the input size. So n is the input size here. If n is the input size, okay, and you want to factorize this integer, okay, which corresponds to this input size small n, and the best possible algorithm will take this. The complexity is this order of n to the power 1 by 3 log n to the power 2 by 3. This many operation. Now, if the size is, let's say, 200 digits or 250 digits, let's say. So if n is, if n is 200, let's say, or 250, okay, then using a machine, okay, or using a computer which can perform 200 millions of instructions per second, okay, 200 millions. I mean, you can check this, okay. I mean, everything I'm saying in terms of approximation, okay, approximately I'm saying. So 200 millions of instructions, let's say, per second. So this is the per second. So this is the computing facility, suppose I have, okay, and this is my input. Then if we compute this at exponential of order of this, then it turns out that in order to factorize this number n, we need 10 million years. So then we need, with this mind, this power, I mean, a computer, with a computer having this many operations per second, let's say 200 millions, okay, and my digit was like n by 250 binary digits, then we would need approximately 200 million, 10 million years, 10 million years to solve this. So this problem is not tractable. Okay, there is an algorithm. Okay, you can, so in principle you can solve this problem, but if the input side is large, okay, if input is small, then it is not a problem. Okay, but if the input size is very, very large, like here 250 binary digits, then it will take 10 million years, okay, to solve the problem. So you need approximately 10 million years to solve this problem. So what is the conclusion? Solve this problem. The conclusion is this is intractable. Practically, it is not possible. Okay, practically not possible.
Sir, I have a doubt. Can you
However,
hear me now?
yes, yeah, I can hear you now.
Okay, so this is big O of, and you told big O of n power 1 by 3 log n power 2 by 3 operations, right? So is that like the elementary logical operations that you were talking about?
Yeah. Number of operations you can also say. Number of operations, yeah.
And we are assuming that each operation will take like 1 unit of time, is it?
Not exactly. So we are assuming that 200 millions of instructions per second.
Oh, okay. Okay, yes, sir.
Yeah, everything is approximate here. Okay, so you can later on, I mean, I'm doing it very fast because I need to get into the quantum computing part. Okay,
All right,
I'm just giving you some, yeah, so I'm just giving some glimpses of the classical computation so that you will understand the need of this. Okay, I am giving you some idea of classical computation where you'll find that, okay, there are some problems, okay, for which I need to investigate some, I need to invest some time to understand quantum computing. Because I said Peter should already have developed an algorithm which needs polynomial resources to solve the same problem. But
yes,
why
sir.
this problem is difficult? So in order to understand that, so I'm just giving you an idea. Okay, so this problem is really a hard problem.
So
By the way,
one more little doubt, sir.
yeah,
So, so yes. So is it proved that the best algorithm can do this in big O of n power 1 by 3,
yeah. Yes.
or is it?
This is the best.
Or it,
No. This is the best possible algorithm. I think it is somebody called Hughes. I think this is a paper, I mean, article from 1998. Okay, I think this
oh,
is the known best algorithm. Yeah,
is it the best known
the well known.
algorithm, or is it like the universally best?
Yes. Yeah.
Okay.
No. Universal best known algorithm means which is discovered. Yeah. Okay. I mean, see. So this is. I'll come talk about this later also. So if I have a problem which cannot. So that's why last day also I talked about that. This problem is hard. Okay. It means it is not like it is not solvable, but the machinery, whatever we have, whatever the best algorithm we have, Using that, it is not solvable. So if it can be proved that there cannot be any improvement of this, okay, then this is be like close to P equal to NP problem, which will come to that, okay, a little later. Okay, so I'll just talk about this a little bit, okay. So I'll talk about that. But this is the, I mean, till today, whatever the best algorithm possible is something like that, which has this particular complexity, let's say. Okay. Okay, so yeah, so if there is anything like somebody discovers like, okay, this problem will be, can be solved, let's say in polynomial time. Okay. So then that will be maybe the best scientific discovery in 900 last 1,000 years. Okay. Because this problem is related to that NP equals to P equal to NP problem, which I'll just briefly discuss, very briefly discuss, because that is also a fundamental problem in computing. Okay. Okay. But so whenever I say that this is exponential means, it does not necessarily mean that whenever it takes, I mean, whenever it takes polynomial time, it is an easy problem. I said it is comparatively an easy problem. We'll call it easy or tractable. But suppose, so this is my first example, but suppose I have a problem or I have an algorithm, okay, which takes, let's say, this is a second example, which let's say this is polynomial time or polynomial resources. So this is also polynomial, not exponential, but this is polynomial algorithm, okay. But this order is, let's say, suppose this mean, what is happening with my pen? So order of, let's say, n to the power alpha, okay, and alpha is very large. Let's say alpha is equal to 1,000. Then also the problem is difficult. It's not that it is it is not difficult. It's a difficult problem. Okay. So whenever I say polynomial resources, you have to understand, I mean low degree polynomial, okay, like n square, okay, n cube, n to the power 4, maybe something like that. It is not like n to the power 1,000. Okay. Then also the problem is really hard. Okay. It's not like it is easy. Okay. Because it will also take a lot of time, for example, if you increase n, of course. Okay, so even if it is polynomial resources, but if we have a high degree of the polynomial, okay, then also in practice, okay, it will be really a difficult problem. Okay, so it is not like it is a clear classification that polynomial means easy and not for super polynomial it means, or exponential it means very hard. It's not like that. Polynomial also can be very difficult if the degree of the polynomial is very high. Okay, but the fundamental question is, does this complexity depend on the model of computation? That's the fundamental question. Okay, so the question here is now, or is it independent of the model of computation? Okay, so the question is, so does this, I mean what I want to say is, suppose this complexity, okay, this complexity is coming because you are solving the problem in, let's say, circuit model of computation. Okay, then this is the complexity. If you use other model, maybe the complexity is less. Is that the question? Okay, or can this happen? Can there be any other model of computation for which the complexity will be less or complexity is small? That's the fundamental question. So is the complexity, or is the computational complexity, or uh, let's say, does this computational complexity depend on the model of computation? And the answer is no. It is independent. Okay, the answer is no. It's a big no. And this answer is, okay, this answer is known as another thesis, which is the same name, Church-Turing thesis, but it is called the strong Church-Turing thesis. Okay, no, because of this, the strong Church-Turing thesis, okay, which says the following, that if a probabilistic Turing machine can simulate any model of computation, okay, in fact, a probabilistic Turing machine can simulate any model of computation with I think at most a polynomial increase in the number of elementary operations. Okay, so that means it doesn't matter whether your whatever your model is. Okay, the probabilistic Turing machine, okay, can solve the same problem with at most an increase of polynomial time. Okay, so yeah, that is what is the strong church thesis. Okay, so that means if a problem cannot be solved using polynomial resources in a probabilistic Turing machine, okay, then it cannot be solved, okay, in any other machine using polynomial resources. That's the crux of this thesis. Okay, so I'll just write it down, the conclusion. I'll not write what is the thesis. So let's say, so if a problem, okay, cannot be solved, okay, with polynomial resources, okay, then resources on a probabilistic Turing machine, okay, it has no polynomials, or it cannot be solved using polynomial resources, okay, using any other model of computation. So this complexity is independent of your model of computation. Computation. And the Peter's source algorithm, okay, on a quantum computer, it can be solved using polynomial resources. And we do not know any algorithm which can solve this factorization problem on a classical computer, okay, using polynomial resources. So if there is a chance that no algorithm exists which can solve this problem using classical computer with polynomial resources, then this quantum model of computation will definitely be powerful than probabilistic Turing machine. And it will definitely reject this strong charge Turing thesis. Okay, so this is just a note I want to make.
Sir, one small. Sir, so what Church Turing thesis mentions is that if a problem cannot be solved with a Turing machine, it can't be solved with any other machine, right?
No. It actually says so. That's why I did not write. No. It does not say this. This is the conclusion I made. Okay, so it actually say. Can you see what I'm writing? Because there's, or the screen is frozen.
Yeah,
I'm writing something else.
other model of I can see.
Just a minute. The screen is frozen. I can see. Just a minute. Just. Yeah, go ahead. You're saying something. Yeah, please go ahead.
Yeah, so what Church Turing thesis says is that from what I understand, it's that if a Turing machine uh, cannot solve it, probabilistic Turing machine cannot solve it, then no machine can solve it. But that doesn't mean that if some circuital model, if classical circuital model can't solve it, Turing machine can't solve it. It's not the other way around, right? So even if there exists no polynomial time prime factorization in classical circuital model, it wouldn't violate Church Turing theorem.
No. What I said is, if you use probabilistic Turing machine, okay, So probability, any probability, I mean, if you take a probabilistic Turing machine model, okay, it can, that exact strong charge Turing thesis, it can simulate any model of computation with at most, okay, let me just write it down, what the thesis said. The thesis said the probabilistic Turing machine can simulate any other model also. It can simulate any model of computation. Doesn't matter whatever the model is. So any model of computation
Yes, even
with
this way, sir. Okay, yeah.
with at most a polynomial increase, okay, increase of, let's say, elementary operations. Yeah, please go ahead. What are you saying?
Yes, even from this statement, sir. So
Mm-hmm.
what this statement says is a probabilistic Turing machine can simulate classical circuital model, quantum circuital model
No, 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 no.
just
So,
additional
so no, no,
polynomial increase, right?
no, 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 no. So here, when I say the probabilistic model, the probabilistic Turing machine model, or the probabilistic Turing, okay, what did I write? Probabilistic Turing model. Okay, it can simulate any model of computation. Any, this is important. I did
Yes.
not say, yeah, any model of, this is a thesis. That means this is an observation. Okay, this is a thesis, means this is a conjecture. That probabilistic Turing machine can simulate any model of computation with at most a polynomial increase of elementary operation. Now, why I'm saying that the quantum model of computation can reject this thesis? My argument is, suppose there is a suppose, okay, assume that, because we don't know whether there is an algorithm which can solve the um, prime factorization problem with polynomial resources. We don't know whether there is or not. If you assume that there is no such, but quantum computation can solve that using polynomial resources. So that means
Yes.
it's a different model of computation. So then that is a different model of computation. Okay. That is a different computer model which is not fitting in this picture. That means there are models, okay, which, I mean, this will reject this. This is what my statement is. There are models of computation which
I'm saying it
violates
won't
this.
reject, sir, because you're saying you are saying that if there is no algorithm which can solve in polynomial time prime factorization using classical circuital model,
Mhm.
uh, it will reject this. But I'm saying it won't reject this because this statement says that Turing model can simulate any other model. It doesn't say that other model can simulate back Turing model, right?
No, no. If that problem, the factorization problem, suppose it cannot be solved by probabilistic Turing model using polynomial resources, then no model can do that, no. But quantum model can do that.
No, this probabilistic Turing machine can still probabilistic Turing machine can still solve prime factorization in polynomial time, but classical circuital model can't solve in polynomial time. This won't reject this, right? This won't reject the thesis, right?
No, that don't reject the thesis, but I am saying the other opposite one. I am saying that probabilistic Turing machine model, that suppose it cannot solve the problem, prime factorization problem using polynomial resources.
Oh, okay. So I was thinking you were saying circuit model can't solve. Okay, yes.
No, no, no.
Okay.
Because everything is equivalent to probabilistic Turing model now. Okay, whatever model of computation it is. So if the probabilistic Turing machine, if it cannot solve the problem, okay. So yeah, so you understood? If it can, so if this model cannot solve the problem with polynomial resources,
Yeah, that
then
I understood, sir. Yes.
okay,
But
okay, okay.
but we can't say that everything is equivalent to probabilistic Turing machine, right? We told that
No, this is
which
the thesis.
probabilities.
This is the thesis. This is the
Yeah,
thesis. That means quantum
even
model of
with the
computation is
thesis.
something different. So so
Sir,
then this will contradict the thesis. That means
I
the
want to
thesis is
clarify
not
this,
valid.
sir. So, yes,
Yeah, go
just
ahead,
one
go ahead.
statement I want to clarify, sir. So the thesis is
Yeah,
saying
yeah.
that
Please go.
using using Turing model, we can simulate any model. That
Yes,
does that mean that
with a possible
from
increase
any
of,
model,
yeah.
yeah,
Go ahead.
with a polynomial, additional
Yeah, yeah,
polynomial,
yeah, yeah.
does that
Go
mean
ahead, go
that
ahead.
from any model we can simulate that Turing model? No, right?
No, 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 no. That does
No,
not mean
right?
that. Yeah. No, no.
Yeah, okay. So that means no Turing model. We can't equivalently say that Turing model is equivalent to some circuit model or anything like that. We can't do that, right?
No, no. Equivalent in that sense that suppose there is any model of computation which solves a problem. Okay. And use Turing probabilistic Turing motion that also solves this problem. So the thing is, maximum computation or operations increase of this maximum is like polynomial. So that's not a problem. So that means if some
Yes.
problem can be solved by, you understood. I don't want to spend much time on this. You understood this.
Okay. Yeah. Yeah. I understood
Uh,
that, but yes. Okay. Okay. Yes.
oh,
Okay,
okay,
sir. Go on.
okay, okay. Yeah, yeah,
I'll ask later if I have.
yeah, yeah. Okay. And the another issue is so one we should know about this classical computation. I think this is the last issue is this is the issue of complexity classes. Okay, complexity classes. So I'll very briefly discuss. Okay, some classes. Okay, so basically what is happening is there are some problems. Okay, as we have seen, so there are some problems. Okay, which are feasible. Okay, which are tractable, and there are some problems which are practically not tractable. Okay, till today, let's say. So then I can divide the computational. I mean, I can divide the entire class of problems. Okay, as follows. Let's say I denote this letter P. Okay, P. The problems. Okay, so I'll say a problem. So this is a class of problems. Okay, this is a set. This P. It's a class of problem. So I'll say that a problem belongs to this class. Okay, so let's say so a problem P is in this P. Okay, this bold P. Let's say. Okay, if P can be solved using polynomial time. Okay, polynomial time. That means polynomial is polynomial number of steps. Okay, and polynomial means polynomials of what in terms of the input size. Okay, then I define another class of problem. So this is a polynomial class. Okay, this is like that. So this class is a polynomial class. This set of problems, let's say. Now I define another class of problems which I'll denote it as NP. Okay, NP. So this is a problem. Okay, whose solution can be verified in polynomial time. So if there is a problem P, okay, which is an NP, it means if P, the solution of P, P can be verified. See, I did not say anything about how to obtain the solution. Okay, whether it can be obtained in polynomial time or not, I don't have any comment on that. But I'm saying if somehow I know the solution, I can verify that it's a solution using polynomial time. So if the solution of P can be verified using or in polynomial time. Now see, if I just compare those two classes, see any problem which is in P is also in NP because the problem itself can be solved in polynomial time. So the solution also can be verified in fact with polynomial time, right? So this P is a subset of NP. So NP class of problems, and this is the class P. So P then, so for example, this factorization problem. This is in NP, but not in P till now. Okay, till now not in P. That's what I'm saying because it is not proven whether there is a polynomial algorithm or not. So this factorization problem, because suppose I give you two integers, A and B. Okay, these are the factors of a number n, let's say. Then you can multiply these two numbers and can check, and the multiplication is polynomial time. Okay, multiplication, addition, these are all polynomial time algorithms. It can either, these are simple problems. So then the solution can be verified in polynomial time. This is okay. So factorization problem belongs to NP. But the question is, does there exist problem in NP that are not in P? And it is a very, very fundamental question in the field of mathematics and computer science. Okay, so the question here is, this is a fundamental problem. Fundamental problem. That does there exist a problem, okay, problem in NP, okay, but not in P. Okay, this is an NP. This is yet to solve. This is an open problem. I mean, can you find a problem which is in NP but not in P? This is an open problem, and the conjecture is P is not equal to NP. And if you can solve this problem, okay, whether this is conjecture correct or not, you'll get $1 million. There is a prize for this problem. So this is a very big problem. Okay. Okay, there are many subclasses of these sets, okay, but I'll not discuss right now. So if I need to discuss, I'll discuss this later. Okay. But there is another class of problems. So this is like in terms of time, let's say, okay, in terms of operation. And now the operation means time because to perform an operation you need some time, right? So it is related. So now let's say in terms of space, okay, so you may need some space means like how many memory cells kind of thing, okay, how many memory. I mean, I think you know a little bit of architecture. So there are something called there are memory cells, okay, where you store this number. So there are registers, okay, memory cells. So you can store these numbers, okay. So space, this is something called space complexity as well. So there is something called space complexity. So how much space is required? Okay, what is the amount of space resources? Okay, and there is a class which is called P space. ACE. So this is a set of problems. So if there is a problem which is in this P space, okay. Okay, that means so polynomial amount of, here also a polynomial means in terms of input size. Okay, like input size means if there is an input, how many memory cells are, how much space is required to store that input. So polynomial, it means polynomial, okay. Polynomial amount of resources or space is required. So I'm not telling you the units, okay? That's it depends on whatever unit you are considering. Polynomial amount of space is required, okay, to solve that problem, okay? And polynomial means it is in terms of input size, okay? Now obviously P is a subset of P space. Why? Because if a problem can be solved, okay, in polynomial time, okay, let's say in a Turing machine, okay, so definitely it will explore means because you need to bring from some, so you need to store some amount of bits into some space, this and that. But since the time is polynomial in a Turing machine, so it can only use polynomial number of memory cells because it has to explore and use those memory cells during the solution of the problem. Okay. So any problem which is in P, so it is also in P space. And it is conjecture that this is again one conjecture that P is not equal to P space. Same problem here also. Okay, P is not equal to, and this is like a problem which has no proof. Like, does there exist a problem in P space which is not in P? It is not known. But P is a subset of NP. Okay, and NP also must be subset of P space. Why? Because NP problem is what? NP problem is the problem whose solution can be verified in polynomial time. So anyway, so when you are verifying, you need only polynomial amount of space again. So it is subset of P space. Okay, P space.
Shouldn't it
But
be NP space or something?
what is that?
Because verifying is the if a problem is verifiable in polynomial time, we call it NP, right?
Yes, yes.
And and the problem is P space if the problem can be solved in polynomial resources, right?
Yeah, yeah.
So there is no direct like relation, right? If it can be verified, doesn't mean it can be solved, right?
No, here verification is the problem. No.
Yeah, exactly. So
So
if it can be
verification.
verified.
So what is the problem in NP? The
No, I
problem
did not
which can,
understand why NP is subset of P space.
because any problem which is NP, okay, NP means what? The problem here is you have to verify whether that is a solution or not. That is the problem here. So that problem is in the NP class. But when you are verifying this, you need only polynomial amount of resources.
But then, if you are verifying, then that's not a P. Then that doesn't mean the problem belongs to P space, right? It can be something like different, right? NP space or something.
Okay, you just think about it. Okay. And if
Okay,
you have
let's
other,
talk.
yeah, you just think about it a little bit. Okay. But this subsets, okay, these inclusions, we don't know, but we don't know whether these inclusions, or let's say this, how do I say it? This subsets are, okay, let's say inclusions, okay, are strict or not, okay. So so that's the that is what I wanted to say about polynomial computational complexity. And now we will talk about quantum computing. But before we start quantum computing, we need to know, I mean, I just want to revise, okay, the four quantum postulates. I mean, four postulates in quantum mechanics. Okay. So this is again a very brief review about the postulates of quantum mechanics. Okay. So the difference between the classical mechanics and quantum mechanics is what? So in the classical mechanics, okay, I mean, ultimate problem is to determine the dynamics of the state of a system, right? System here means it could be like one particle, two particle, or in general n particle system, doesn't matter. Okay. So here, so whenever I refer to system, okay, so it corresponds to, let's say, in general n particle system. Okay, and then gradually whenever we say one particle, two particle, we'll talk about it. Okay, particle system. And in classical mechanics, okay, the states of a system of n particles, okay, this can be determined, okay, if you know the initial positions, or if you know just the positions and the velocities. then it can be solved using the Newton's law of classical mechanics. Okay, so the systems in classical mechanics, in in classical mechanics, okay, the system can be known, the states of the systems okay can be determined from the positions of each of these particles, position and velocities cities what is velocities of can be determined from the positions and velocities of the particles using Newton's law. Okay, Newton laws of classical mechanics. Okay, in principle, let's say, means I'm not discussing how it can be done. But quantum mechanics actually is a very different setup. Okay, where we always start talking about some postulates, because I mean there are some axioms. Okay, what is a state, how is state evolved, okay, and so on. If you want to discuss that, we have a basic set of 4 postulates, okay, which describe how to manipulate a quantum system. That means you want to get some value from a quantum system and how to do it. What is the state of a quantum system and how does it evolve? These are the 3 things, okay, which are described by these 4 postulates. And the first postulate is okay. So the state of a system. So I'll just recall system by system, I mean in particle system. Okay. So state of a system here, okay, is described by a vector. And in fact, it is a unit vector. Unit vector, we denote it by ket psi. Okay. So in mathematics, when we say vector, okay, we represent it by either a column vector or row vector. But we are using this notation ket. It means, okay, in principle, it is a column vector. Okay, so this is a column vector. Whenever we write ket, it means it's a column vector. This is a column vector. Okay, and this column vector is, in principle, it require a Hilbert space, but for the purpose of this course, we will only assume that it belongs to C to the power n. That is enough for us. C to the power n means, which is a complex vector space. So C n times Cartesian product of C itself. Okay, like R to the power n, the vector space. So you have C to the power n, and of course C to the power n is equipped with an inner product. Okay, so a vector psi which belongs to, so this is a unit vector from C to the power n which belongs to, this is for the purpose of our course, but in general, people will define it from a Hilbert space. I don't want to go to why you need a Hilbert space and so on, okay? Because we don't need that, which belongs to C to the power n. That's it. So this is a unit vector from C to the power n. And how does it evolve? So the first postulate also says, how does it evolve? So that how does it evolve means if the state, if psi at t, this means at time t, psi t, ket psi is the state. Okay. If this is the state uh, at time t, how does it evolve? The evolution, this denotes the state of the system at time t, then the evolution of the system is governed by something called the Schrodinger equation. Schrodinger equation, which is as follows: I h cut d dt psi t is equal to h psi t. This h in our case, so this is called Hamiltonian of the system. But in our case, for the purpose of our case, we need only to know that this is a matrix which is Hermitian. In general, this is called a self-adjoint operator, okay, which is the Hamiltonian of the system. So this is known as, so that's why the sign, that's a symbol, it is written, denoted as H. H means it's Hamiltonian of the system. But for our case, we'll say that this is just a Hermitian matrix. Hermitian matrix. And see, this is a very simple equation because it is a first order differential equation. We can directly solve this if the initial state is known. Okay, let's say initial is means t equal to some t that is known. This is just a faster ordinary linear ordinary differential equation. It can easily be solved. And then h, this h cut, this is h by 2 pi. Okay, where this h is the Planck constant. The Planck constant. And even if you don't know, that is perfectly fine. It is just value as constant, whose value is like, this is approximately equal to 6.626, I think 10 to the power minus 34 joule second. 34 joule second. Other it is fine. Otherwise, or if we just type in Google what is the Planck constant, okay, so you may learn a little bit more about this. But for our purpose, okay, it is enough to know that it is h cut is a constant which is related to something called Planck constant. That is enough. So this is, I think today we have to stop here. Anyway, so this is the first one. So first postulate talks about the state of a quantum system and how does it evolve. So it gives the evolution. Okay, it describes, this is described by the Schrodinger equation, and which is very easy to solve. So I'm not going to solve what is this. This is just the first order differential equation. So the solution will be like psi t will be equal to e to the power minus iht. That's it. Iht psi, so whatever psi 0. Let's say that's the initial solution. So it is one line. So yeah, so this is what it is. Yeah, so if you have any questions, somebody was asking some questions, and now we can talk about that. And others, you may leave if you have some work or some class. Otherwise, you can just ask if you have other question. You can please ask. Yeah, go ahead.
Yes, sir.